Hey, welcome back. In this video, we will understand what time complexity and space complexity, or in general what asymptotic analysis mean. So if you remember, in the last video, I said we need a way to analyze these algorithms without these external effects. This process is actually called as asymptotic analysis. So let's take example of how this works. Okay. So here is a program as an example which calculates the sum. Okay, sum of a number. For example, if I give 5, so it is 1 plus 2 plus 3 plus 4 plus 5. So it will give us the sum of the number until that number. So here's the option 1 of the program. Here we just use the mathematical program which we learned, or mathematical formula which we used to calculate the sum of n numbers during our high school, right? It's n into n plus 1 divided by 2. Okay, so this is one method to calculate the sum of a number. Here is the option 2. What we do here is like we initialize a variable sum is equal to 0, and from 1 to until n we just add it to the sum. So we loop through and add it to the sum. Here is another approach. So let's see what is the option 3. So here as well we initialize the sum as 0, but then we run a loop inside a loop and then increment the sum by 1 each time, and then at last we return the sum. So which program is the best? Obviously you would say option 1 is the best, correct? But we need a asymptotic analysis or mathematical proof to prove the same. So let's try to do that. So for example, if you see here, we are doing some multiplication and then some addition and then some divisions, correct? These are all constant amount of work. Multiplication, addition, these kinds of things. So in the overall, it takes constant amount of work. Okay. So let's take the example of option 2. Here as well. So we initialize the sum as 0 and then we run a loop from I to n, and inside this loop, if you see, we do a sum is equal to sum plus I. This is a constant amount of work, but this constant amount of work is run n number of times, correct? So hence we say the total amount of work is n times, or n into constant times. Okay, this is the option 2. Now let's take the option 3. So we initialize the sum as 0, and inside this loop we run until n, and inside this another loop we have a nested loop from j which runs from 1 to I, and inside this we just increment the sum. Incrementing this sum is constant amount of work, but how many times this constant amount of work is performed? It is done I or n times n, right? So this runs n times, whereas this will also run not exactly n times, but each time one lesser, right? But still we can take it as n square times. So you see, this is constant time, this is n time, and this is n square times. Okay, through this way we could see like this is really performant, but I am saying this n square and constant time. Is there a way or notations for denoting the same? Yes, we do have some methods to do the same. We do something like, log n power 1 by 2, n square, n cube, n power 4, 2 power n, and n power n. And you could see like here I'm missing the constant. Actually constant is more performant than log n, and log n is more performant than n power 1 by 2. N power 1 by 2 is more performant than n, and n is more performant than n square, and so on. So you could see then we could say, right, according to this notation, this performs poorer than this, and this option 2 performs poorer than option 1. So in order to segregate all these things, right, we also have 3 other notations. It's called probably best, worst, and average cases. The 3 notations are big O notation, theta notation, and omega notation. These are used to signify the order of growth of an algorithm. Okay, big O is also known as worst case time complexity, and theta is also known as best case time complexity or average, I would say. Best or average, and omega is the best case time complexity. Okay, so what do I mean by worst case, average case, and the best case? Let's see using this example. So let's say we are again calculating the sum, but this time we are passing an array itself. Okay, now inside this sum method, I'm initializing sum as 0, and for let I is equal to 0, I less than an I plus plus. So we are running through a loop and then calculating the sum. Okay, so we just each element of array is added to the sum, and at last sum is returned. So in this case, if you see, the worst case, best case, and the average case all are n times, because this loop will be running n times irrespective of the input. But let me delete this. Let's take this as an example. Now what we are doing is, if you see, for the past array, we are getting the length of the array. Now if the length of the array is less than 6, I'm just returning 0. If not, we do this n times operation. Okay, now how do you analyze this program, right? What will you say this complexity, or what is the analysis you would say? How we can't say n times, or we can't say it's a constant times, right? This is where this big O, theta, and omega notation comes into the picture. Okay, so now what we will say is, like, on the best case, what is the best case notation? It's omega. Okay, best case is whenever the n is less than 6. So we are doing a constant operation. So we could say the time complexity of this algorithm, time complexity meaning the time taken to run, okay, is omega of 1. The constant time is also called as 1 as well. So we say omega of 1. Got it? Now coming to the big O. Big O is the worst case analysis. So on the worst case, what happens? N might be greater than 6, which means we will be running this loop for n times. So which means the worst case time complexity, we call it as big O of n times. Okay, big O of n. Big O is nothing but that normal O, capital O, you could think it of. Then you might ask, what is this theta? It's the average case. What we say here is that there is a 50% likelihood for this case, which is the best case, as well as 50% probability for worst case as well. So on average, it takes theta of n times. So on average, theta of n times, which means it could be constant times or it could be n times. Okay, great. Now we talked about this time complexity, basically how much time it takes to run. Okay, and in the industry, prevalently omega notation is not being used. Mostly, like, we avoid using omega notations because there is no point, right? There is no point in calculating the best case alone, because more than best case, we are worried about the worst case. So hence, as I said, we worried about worst case, we mostly use this big O notation. But theta notation is also very much used. That is, for example, in the case where, let's assume, we don't have this if condition. Okay, then we know, irrespective of worst case or best case or average case, this is going to run n times exactly. So when we know the exact time complexity, we will use this theta notation. Again, we will ignore omega because omega is not used much. So when we know the exact time complexity, you use the theta, and when you know worst case and the average case, then you use theta or worst case scenario, okay, which is big O. Mostly we will use big O. So in this course, let's stick to just big O alone. Even though we have this exact notation, in some instance we will still use big O. That's no problem, because big O encompasses average case as well. Okay, great. Now what is the space complexity is all about? See, as I said, time complexity is nothing but how much time this loop is running, right? So I said it's big O of n. And in a similar way, rather than counting this number of loops or something, how much space it is used is called space complexity. But remember, space complexity doesn't include the initially passed input parameter. Okay. So in this case, if you see, we are just having one or two constant space complexity variables. One is like n, which is like a constant, and sum, which is like one variable, right? It's also a constant. So we would say it's big O of 1 space complexity. Then when will we have more than or greater than big O of 1 space complexity? For example, let's assume I also have another variable called let copy array. Okay, and whenever I'm looping through it, I am pushing each element of this array into that copy array. Okay, in that case, if you see, we are creating another space that is equal to the array length, correct? Which means we are having the space complexity of big O of n. So that's how we calculate the space complexity. Got it? So in this video, we talked about this big O, theta and omega, and we said like we will only concentrate on big O, as well as we saw some overview about time complexity and space complexity. Great. So let's continue in the next video.